All right, let's get right into it. We're going way beyond the introductory stuff today, diving headfirst into the world of high-performance, banking-scale Java systems. Think of this as your production playbook for Java collections, the real-world guide for when good enough just doesn't cut it. So let's be super clear right from the get-go. This isn't your typical tutorial. We're talking about systems that are processing millions of records, all under really strict SLAs. This is for all of you working in the deep end, where things like high concurrency, data audits, and the constant pressure of garbage collection are just your daily reality. You know that in these environments, the wrong choice doesn't just make things a little slower, it can literally bring an entire system crashing down.
And this quote, it just hits the nail on the head. We're moving past academic theory and into the messy, complicated world of critical trade-offs, real-world failure modes, and what it actually takes to make the right call when you're operating at a massive scale.
Now, here's something that might actually surprise you. Before we even think about which collection to use, there's a much, much more important principle we have to get right. And honestly, this is the one that when people overlook it, becomes the root cause of most production disasters. I'm talking about the lifetime of your data. So here's the absolute key takeaway. Java collections are not databases. Let me say that again. They are not meant for long-term storage. They are in-memory working sets. If you just ask yourself this one question first, how long is this data going to be around? You can prevent an entire class of production nightmares before you ever write a single line of code. And this slide just illustrates the point perfectly. Look on the left, that's the safe workbench pattern. The code creates a new list for a single job, it does its work, and then the list just disappears when the request is done. It's safe, it's predictable. But on the right, that's the dangerous warehouse anti-pattern. That static global cache, it just grows and grows and grows. That's not a cache, that's a memory leak just waiting to happen. Okay, so once we've established that our data has a short, predictable life cycle, we can finally move on to the next step. You see, senior developers don't just randomly grab a collection because they know its name. They run through a mental checklist of how the data is actually going to be used. It's all about the access pattern. And what's so great about this checklist is that if you just answer these questions honestly, the right collection practically chooses itself. For example, if you answer yes to do I need a key value lookup, and also yes to will this be shared across threads, well, you're immediately pointed directly at concurrent hash map. If you need a specific predictable order for something like an audit, you're probably looking at a linked hash map. This checklist is what turns a wild guess into a deliberate, correct engineering decision. All right, now that we've got that new mindset locked in, let's really dive into the playbook. We're going to revisit some of the most common collections, but this time we're looking at them through the eyes of a system architect who's obsessed with performance, trade-offs, and avoiding those nasty failure modes. So ArrayList, it's often the default choice, and for a really good reason. It is incredibly fast. Why? Because all its data is stored in one big, contiguous block of memory, which is something modern CPUs absolutely love. It leads to great cache performance. But that speed comes with some very, very strict rules you have to follow at scale. Just look at this comparison. The code on the left where you're removing items while looping through a list, that is a performance disaster. Every single time you remove an item, you could be forcing the JVM to shift millions of other elements down one by one. The correct pattern on the right is to just filter the items you need into a new list. It's clean, it's fast, and it avoids all that expensive data shifting. And hey, notice that other pro tip in the correct version? Pre-sizing the new list. That's a critical optimization to avoid the list having to constantly resize itself. I absolutely love this quote because it is so true. Linked lists might seem like a good idea in a textbook, but in a real system, its performance is usually pretty terrible. All that pointer chasing it does, jumping from one memory location to another, is poison for CPU caches, which thrive on predictable, sequential memory access. And this diagram shows you exactly why. The linked list has its nodes scattered all over memory. The CPU has to jump around constantly, which leads to cache misses and slows everything down. The ArrayDQ, on the other hand, keeps everything in a nice, tight, contiguous block, just like an array list. That makes it way faster and much more memory efficient for any kind of stack or queue operation. Okay, let's talk about maps, because this is where a lot of systems either succeed or fail. HashMap is the absolute king of speed for single-threaded work, but the instant you share it across threads, you have to switch to concurrent HashMap. And here's the key. It's the default for shared state, not because it's always the fastest, but because it's designed to fail safely when things get intense. Oh man, this right here is a classic concurrency bug that has brought so many systems to their knees. That if contains then put pattern on the left, it looks so innocent. But just imagine two threads hitting that code at almost the exact same time. Thread A checks, sees the key is missing, but before it can do the put, thread B swoops in, also sees the key is missing and does its put. Then thread A finally wakes up and does its put, completely overriding whatever thread B just did. That's a race condition. The correct way, compute if absent, is atomic. It guarantees the entire check and put sequence happens as a single, unbreakable operation.
Okay, let's shift gears a bit. We've talked a lot about performance, but now let's talk about something even more dangerous: correctness. We're talking about the silent killers, the bugs that don't crash your system, but instead quietly corrupt your data. These are the kinds of things that only get discovered during a very stressful audit, months or even years later.
This is such a great way to visualize what happens if you use a mutable object as a key in a hash map, and then you go and change a field on that object that's used to calculate its hash code. That object can become completely lost. You can't find it, you can't remove it. It's now a ghost in the machine, a permanent memory leak.
So, these are the unbreakable vows. These are the rules you simply cannot violate when you're using hash-based or sorted collections. Number 1, mutable keys are absolutely forbidden. Number 2, the contracts for equals and hash code have to be perfectly maintained, always. And number 3, for sorted collections, your comparator has to be consistent with equals. If you violate any of these, you're not getting an exception, you're getting silent data corrupt.
All right, let's pull all of this together now. We're going to synthesize everything we've talked about into a practical, actionable framework that you can start using every single day. This is how we start thinking like a true system designer.
And here it is. This is your cheat sheet, your new best friend. When you get a new requirement, you just map it onto this matrix. Do you need shared mutable state across threads? Boom, that's concurrent hash map. And remember to use those atomic operations. Do you need to process items in a producer-consumer setup and manage system load? Blocking queue is your answer because it naturally handles back pressure. Need a deterministic order for an audit log? That is a perfect use case for linked hash map. This matrix turns complex architectural questions into clear, direct, and defensible answers.
And really, this is the ultimate point of all this. When you start thinking about collections in terms of their memory layout, their concurrency models, and their specific failure modes, you've made the leap. You are no longer just a programmer using a framework. You are consciously and deliberately designing robust, scalable, and correct systems. You're a system designer.